with Francois Pachet, who will discuss some experiments in creating
Thank you. Thank you all for being here. Thanks, Cedric, for inviting me. I have to say, firstly, that I'm not a mathematician. It's quite clear. I'm not either like a physicist. I'm not a statistical physicist. But these things have a lot of interest for many of the subjects that you are discussing here. But I'm mostly an AI researcher. And don't ask me what is AI, I'm not sure. I think AI is really about trying to identify problems that humans can solve, more or less, but for which there are no well-defined algorithms. And if you take the definition of AI, of course, the domain seems to shrink a lot with deep learning, and I'll try to show that it's not the case. And I talk about creative sequence generation. Don't ask me what creative means. Let's say interesting sequences, but you will, I think, understand what I'm trying to do. And I want to say also that I've been working for a long time at Sony, and most of the things I will talk here were developed when I was at Sony with an ERC project called Flow Machines. And then I left Sony for Spotify, went to the industry, the big bad guys, and then I left, and now I'm just doing stuff that I think are interesting. This is why my affiliation is my GitHub project. I try to implement stuff and put them there so that people can.
But you have some affiliation also to Sorbonne University?
I am a member associate. So Flow Machines were the projects finished in 2018. I want to mention why flow machine. It's a flow, it comes from the flow theory by this guy called Csikszentmihalyi. So it's a Hungarian name, he's an American guy, he's a psychologist, he's dead now. And you know, he has developed, he has written a number of books, some of them are pretty much like self-psychology, you don't have to read them. But there is one book which is really interesting, the one on the flow theory, what you call a theory. It's a theory without theorems, but okay. Basically, in his theory, you have two mental states, which are boredom and anxiety. It's not a very pleasant idea, but in fact, it's very interesting. He says basically, when you do something, you have skills to do what you have to do, the task, and either you are overskilled and you are bored, or you are underskilled, you are anxious. And then in the middle, there is a zone that's called the flow zone that he has been studying for a long time, 20 years, like interviewing a lot of people, mathematicians, but also people doing mundane stuff like cleaning, or tennis, or guitar. The people who have a lot of skills in their domain, and who are able to enter this zone of flow where time stops and you are totally absorbed in your thing. And he has tried to characterize this, in particular, showing that it's an autotelic activity. Autotelic means that you set your own goals. So you do it because you want to do it, you don't do it because you want to please your teacher, your parents, or because you want to earn money, or because you want to be famous. You do it because you are just deeply interested. So it's a one-to-one relation between you and the thing. So it's very interesting. And sorry? No.
Sounds like he was in the zone too.
Sorry?
He was also in the zone.
Maybe.
Yeah,
probably. I think you guys, math is typically the domain, otherwise it's painful if you don't like it. And then, anyway, so the flow machine idea was to say, can we build algorithms or machine systems, especially interactive systems, that are such that people, you play with these things, engage in creative activities, and then they get into the flow thing. So that's the origin of the project. But I think what I'm trying to do, I probably fall under this umbrella of this idea by Daniel Kahneman of System 1, System 2. Do you know this thing? No? Yes? Un peu? So it's a book.
It's in English it's called Thinking Fast and Slow.
Yes, so this is just the book,
Yes, here it is.
the book he has written. So basically his idea is also quite vague, but it's to say that the brain has two modes, mainly one which is very fast and very large. You can answer or take decision on mostly any domain, but very, very quickly. And then the other one, is more slow, and then this is where you try to think and say things which are true and check that what you do is correct and search for solutions. So there is a famous example: if you have a baseball bat and a ball, and the price total is $1.10, and you know that the bat is $1 more than the ball. If you think very, very fast, you say, okay, the price is $1, but then you realize it does not add up. But if you think a bit more, you realize the price is $1.05 for the bat, and the ball is 0.05 cents and 5 cents. Okay, so you see this, and I think it's a very interesting idea. Why? Because there are many domains where it occurs. I take chess, for instance. So chess, you have blitz, especially fast blitz, like 1 minute. I played a lot of blitz because precisely I don't have to think too much. It's about the reflex that you have. And then you have the opposite is not chess that it's correspondence chess, because there is no time limit. By the way, the world chess, the best chess player in the world is probably not Magnus Carlsen or Kasparov. It's guys that you don't know. So in the 40 years ago, he was a guy called Berliner. He was a champion of correspondence chess. And this was considered to be the best player in the world, because he doesn't have any time limit. They can play for 2 years.
But this was before the computers take over.
Absolutely. Now there is a guy called Joe Reynolds. I had to check him out. He's the current world champion of correspondence chess, but of course now they can use computers, so it's a different game. But anyway, just to show that there is an opposition between taking fast decisions like in blitz and thinking as hard as you can like in correspondence chess. And AI today is divided also. I mean, I'm talking about AI research. More or less into these two categories. We have LLMs, deep learning. So if you think about ChatGPT, it's really system one. In some sense, it goes very fast. It's sampling, so it doesn't never think. I will come back on that, of course. But it does not solve hard problems, right? And then you have all the works on combinatorial search, problem solving, stuff like that. SAP solvers today. And a few years ago, I mean, just before deep learning, the tsunami of deep learning that we know, the main area of AI was really SAT solvers and how to solve very, very hard problems, NP and phase transition and things like that. Now it's less, fashionable, but it's still there. It's still there. There are still most complex problems cannot be solved by LLMs or by, let's say, transformers or stuff like that. And so I work a lot on this CSP. So what we call CSP is constraint satisfaction problem. So it's a very general formulation of a combinatorial problem. Basically, you have a graph with variables which have domains, and then you have constraints holding on variables. The constraints can be binary, ternary. So for instance, you could say that y over x is greater than y, it's a constraint. You can say that x, y, z, and so forth are all different. So there's all different constraints. So you have a lot of, the idea that you set up all these constraints, and then you have algorithms that try to find all solutions. well, not only like one solution, but all solutions, and that can also find optimal solutions. It's called branch and bound, right? And again, I will stop talking about CSP, that this has been extremely successful not so long time ago. For instance, the port of Singapore is entirely handled by CSP technologies, because the problem is to find an optimum scheduling of the ships which come and the containers, where should we put them, to minimize their movements, and each improvement in solution is tens of millions of dollars, right? So in those kinds of cases, you don't want us to sample one solution, you really want the best one, and it's very hard. And there are techniques to do that, right? And so I'm here really to show you some examples. I will not do any kind of math, but I want to show some interesting examples of this in music. So for a few years ago, actually, oh my God, it was 20 years ago, no, not 15, 40 years ago, we were interested in following problems. So we were interested in Markov models. I will come back on that later, but Markov models, not order one, but like any order, what we call variable order Markov models, which in fact are quite powerful, but not, of course, as powerful as transformers. But we wanted to generate finite sequences, like sequences of nodes, of chords, of whatever, which had some specific properties that were not Markovian. So for instance, I give you a very simple example here of what we have tried to do. We did what we call the Boulez blues. Sorry.
We are using our system.
I know, you are too smart. Be stupid, please, for 1 hour while I talk. I know it's hard for you. No, I will give the example, and there are lots of papers we can discuss after, if you want. But
so this paper is called Constraints.
This is a journal called
Constraints. This is a journal called Constraints. Okay. You have a journal which is only about constraints.
Absolutely. Well, most work on SAT is there.
I see. Yes.
And so
the whole world, we're not familiar with it.
I know you're not familiar. I'm trying here to to do a little bit of publicity. But this is a domain which is in charge of solving hard problems and finding usually optimal solutions to hard problems, right? And so the example I want to give here is, okay, we have a Markov model. I will give directly the example, which is trained on the chord sequences of Charlie Parker. Charlie Parker is a jazz musician who composed a number of tunes, right? And he composed a number of blues songs. And so we trained the Markov model on that. So the Markov model, in first approximation, it will learn the transition from one chord to the other, like what are the most probable transitions and stuff like that. Basically, you can see it as a matrix if it's order 1. But then we want to generate a sequence which is not like only 2 chords, which is, in this case, 12 bars, so 24 chords, because we want 2 chords per bar. We want the most probable. By the way, if you have a Markov order 1 model and you generate a sequence of length n, you can find the most probable sequence by using dynamic programming or Viterbi or that kind of stuff, which is something you cannot do with a transformer, because the context size is much too long, right? So we want the most probable, but we want also to impose some constraints, like we want it to start by a C. This is C7, that's easy, start by what you want. We want it to end by a G7, this is much more difficult, and with the F in the middle. And we want all the chords to be different, and that is very hard. It's called the all-diff constraint, right? So you see what we're trying to do is to do things which are a little bit contradictory. We want to have a Markov chain, so with probable transitions, but we want to impose a constraint that is a bit crazy, where we want all the things to be different, right? It turns out this problem is actually very hard. It's not hard to have 24 chords all different. It's not hard to have a Markov sequence. It's very hard to have both at the same time and to have the most probable, right? So this is the result, by the way. So you see it's a blues, it starts by C, so I will play it, ends by G7 for those who But you are supposed to be all musicians, right? We are the quarter. So G7 resolves nicely to C, and in the middle there is a F. So it's typically a blues structure. But here you have all chords, all minor chords in all keys, and all the 7 chords in all keys, so 12 and 12 is 24. So you have exactly one occurrence of each chord in the space. And it's the most probable. That is, according to Markov.
His signature.
It's well, it's most probable in the style of Charlie Parker.
Right. And this Charlie Parker's kind of signature. Or
yes, but so why I wanted to do this, because I have this intuition that interesting, I don't know what it means, but maybe can be the solutions to problems where we have very conflicting constraints, right? Things which do not really go together. So I play humans people playing just the chord, the sequence. C7. Locally, it's all very reasonable what you hear. It's all completely standard transitions. What is not standard is the fact that you have all different chords. Most blues, you have 3 or 4 chords. 5. Okay, so that's what I mean by interesting. This is I'm not going to have a hit with this, but this is a very unique object. The most probable blues by Charlie Parker. Enforcing this crazy property. This, by the way, I call it eco-Z tetraphonic, because eco-Z is 20, tetra is 4. So it's not dodecaphonic, it's a 24-phonic music. Okay, it's a joke, just to make fun of your car. So it's a stylistic singularity, if you want. So basically, the idea is going to be, you have a style which is represented by a probabilistic model of some sort, and then you're going to put constraints to explore it at its boundary, or in various ways. So now, what I want to do is to go back to the example of Kostis yesterday. I don't know if you were there. He gave a very interesting example of the genesis. He asked ChatGPT, can you write the genesis with sentences all starting by A, letter A, right? So I did it. And it works, as you can see. I mean, there is only here the 6 first sentences. But what's interesting then is say, okay, I want the second letter of the word to be A, and you see it works almost. Okay, and then what about the 5th letter? 3 errors, so like 50% of error. It's not very good for a problem like that. You agree? It's not a very hard problem.
I have a question, because the same idea. I remember being very frustrated at some point trying to have him write in Alexandrin verses.
I will come back to that.
And he was very bad with counting the syllables.
I will exactly talk about that. But now I will do something which I think you think is easy to do. So there are 4 errors, so there is also.
So you make an error also.
But be stupid, I told you. I mean, please, relax. The exam is tomorrow. Okay, more interesting, start and end with the same letter, but I don't say which one. It's what we call a binary equality. Equality between 2 variables or 2 objects. And you see 3 errors, 50%, but then if I do more, don't tell me it's wrong. If I do more, it's it's only one, there is a second line which is okay, E and D, and everything else is wrong, okay? Don't check, it's okay, trust me. And now the question is, why is it wrong? And what I'm claiming is wrong because the problem is actually extremely hard. It's a very hard, not very, we can discuss it, quite hard to be a problem. Actually, no, don't count.
In the example given by Kostis in his public lecture, actually he even asked not only all lines start with the letter A, but all words start with letter A.
Okay, all words. Okay, fine.
So it was even stronger. Like all variety, articulated, aggregate, argue, etc.
So what I'm claiming here is that the binary equality is hard because you don't know, first of all, you don't know how many letters you are going to have in advance. They all have different numbers of characters. And it's hard because, in fact, so this ChatGPT is not a Markov model, again, it's a transformer. But let's suppose that transformer and Markov model are more or less the same thing, because it's basically a probabilistic model. You have a context size, and it predicts the next, right? By the way, Markov models and transformers are both instances of what they call a recurrent neural network. So it's a network which is greedy from left to right, so you add, and so forth, right? And so we were interested at some point in Markov and binary equality because in music it makes a lot of sense to do this, a lot of sense. For instance, if you want to generate a chord sequence as I did before, usually at the end of the sequence you have either the same chord at the beginning, whatever it is, or you have a chord that resolves nicely because you are going to play in loop, right? So if you start by C, at the end you can have a G7, for instance, or something like that. And if you have a matrix, I will come back on the matrix, it's quite interesting. You want to impose that on a strong beat, you have this or that. So you have to have constraints which are, let's say, positional. And so what we have shown, which is an exercise for you for this afternoon, is that if you want to find to sample from a Markov model, even order one, that satisfy an arbitrary set of binary equalities, so I tell you I want the first one to be equal to the fifth and the third one to be equal to the 25. It's NP hard. It's NP hard. Do you see this? Do you see why? So there is the proof is actually extremely simple. To prove it's NP hard, you have to prove that any Markov plus binary equality is equivalent to a CSP, a binary CSP, which is NP complete. So in one sense it's very trivial, but in the other sense it's very easy. You take any CSP, binary CSP, you can always linearize it.
François, go a bit slower, please.
I will never
this audience is not, this audience is not so much as versed in algorithmic as you think.
Yes, no, but so, okay, if you want, but there is lots of, if possible, there is lots of things I want to show you, and then we can discuss on the details. But so I'm trying to say, if you have a binary CSP, which is an instance of an NP complete problem, that's a problem. If you can solve binary CSPs, you can solve all the difficult problems. I mean, it's a conjecture, but most people think that NP is not P. Then you show that you can transform this problem into a Markov plus binary equalities problem. Right? It's equivalent. How you do? You just traverse you do a Eulerian, in English, Eulerian path that goes through all the vertices. But it's very easy because when you encounter a node that you have already seen, you just replicate it. You replicate it, and then you assign an ambiguity between this node and the previous occurrence. Okay? So it's very easy to do.
Eulerian, like in the Königsberg.
Eulerian means that goes through all the vertices. Not, and it does not. It can go. So you can go several times on the same node precisely, and then you add the quality. So you can do this on any graph, binary variable. And therefore, if you can solve this, you can solve this. So this isn't P complete. It's sharp P complete. There are details. It doesn't matter. But what I want to say here is that the something that seems to you and to us actually very simple, start and end by the same letter, for instance, is actually already NP hard, even with a one-order Markov model. Okay. I am cheating a little bit here because in the proof we consider arbitrary binary equalities. Like this, you say that this is equal to this and this, so they are here, they are crossing, right? So if they are not crossing, it's not NP, but it's very, it's polynomial, but like it's a big polynomial. So in practice, it's really hard to compute. In life, everything that is more than n log n is in practice exponential. No, that's true. I mean, okay, that's not such a But so anyway, so it's polynomial in some cases, but not in general. And so that's why ChatGPT cannot do this. I mean, if he could do that, I would stop everything. I would stop doing research, because it would be that it would mean that NP not only is solved, but NP is equal, not even P, NP is equal 0, because the sampling is, as you know, almost free in terms of computation. Okay? So it's, okay, binary quantities in half. Special case, non-crossing. Okay. Now I want to come back to this thing which I call positional constraint. Please have an A at position 10, or please have a C sharp minor at position 20, that kind of stuff. We are still in a Markovian context because it's simpler than transformer, but it's the same idea. So it is also non-trivial, I mean, to do actually, and most people don't realize it. So I will give you an example, a musical example. So here you have a jazz player, Stefano Di Battista, playing a tune called 90 Tunisia, and then there is a break. So at some point, so it goes like one, like that. On the first beat, it starts to solo very fast for 4 bars, and he ends exactly on the right note. And everything is improvised. That's very hard. It's not hard to improvise when you are a jazz musician, you know, blah, 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 I can do it. But it's very hard to improvise having a goal like this in the future. It's not Markovian. It's not transformatorian. It's hard. So I give you an example of Stefano Di Battista. Okay, so the right note, I don't know which note. This is very hard. How can you do it? It turns out it's not that hard to do it, but it's not trivial. And no way transformers can do this today. We have the proof, we have tried with A and stuff like that. We use, sorry, I have to skip a bit because I know you don't like it. We use something that you guys have invented, which is called belief propagation. Do you know belief propagation?
Belief propagation.
Everyone knows?
Not everyone.
Well, okay. So, belief propagation is the idea that you have, oh my God, I didn't know I had to teach that. You have variables, and they are connected by relations. And you want to compute the marginals of the variables. You want to know what is the marginal of each variable, given that each variable has a, let's say, priors, and there are some interaction or connection between two variables. Typically, a Markov model would be an interaction between two variables, saying that the probability of this is conditioned by what there is before and stuff like that. So here it's only binary relations, but in belief propagation you can have arbitrary relations. And there is a very nice algorithm, very simple, to compute this. It's not a trivial algorithm, you know, it's really part of these things which look simple, but it's really hard to understand. But basically, you send the information in the network forward and backward. And magically, at the end, you have the marginals, more or less. This is a whole chain of work that started with Judah Pearl, the guy who invented Bayesian networks, which is exactly this, and then it was reformulated in many ways. There is sum product networks, for instance, which is the same thing. Belief propagation is kind of the same. All these things, basically, you have variable, probabilistic with probabilities, connections between variables, and you try to compute the marginal, and it works, of course, if the system is well factorized. I mean, if you have interactions all over the place, the algorithm can work. And so if there is no cycle, in particular in that graph, belief propagation guarantees that you have exactly the marginals, exactly as they should be, and the complexity is reasonable. I'm not sure exactly what it's going on.
Your belief is about what the amount of plausibility that you put in various statements depending on each other.
Yes.
And when you become more convinced that something is true, you want to know how it influences your other opinions in the rest.
This is the motivation for Bayesian networks. But then it was kind of extended and to handle more or less anything, you know. It's not even a belief, but you know, any kind of interaction with probabilistic biology. So I will not teach the algorithm. The algorithm is written here. It's like two different kinds of stuff. It's really simple. It's a recursive algorithm. Okay. So basically, sorry, I skipped this because I want to stay in the context of first order, because when you do variable order, it's a bit tricky to combine those two. But basically, the idea is very simple. You have this Markov model. You want to impose positional constraints in the future. So you build a belief propagation graph that includes the whole sequence, and you assign at the position where you want some value, you assign a factor that tells you one hot factor, you know, that tells you this value is 1 and everything else is 0, okay? And then this thing is propagated back, I mean, all the way. And then you get the marginal for the first variable. It's a very simple algorithm, but it's extremely smart, because what it does, it back propagates all these constraints wherever it has to be propagated. So for instance, so we have a couple of papers on that. If you want to generate a sentence ending by France, well, the prior or the first word is not going to be the same that if you want to generate a sentence that ends by anything. So you have to know this. Okay, so this works perfectly, by the way, and it's you can do it in real time, which is what I do. I give you an example with integers because you are mathematicians.
But mainly analysts are more about the real numbers.
I'm a bit ashamed, to be honest, to be here because it's like an imposture. But anyway, you have a train sequence, which is 1, 2, 3, 2, 3, 4, so forth. So it's a staircase thing, like this, goes from 1 to 10. I hope there is no mistake. And you see this staircase going up. Okay? So you build a Markov model from that. So the Markov model will tell you that if you have 5, for instance, you can go to 6 with some probability, and to 4 with other probability, and stuff like that. And now you say, okay, I want 20 elements. I will tell you why it's written 22, it's 20. I want to start by 1, I want to end by 10, and I want a 6 in the middle. And I give you 2 hours to do it by hand. And I want all the solutions. And what I want is not one solution. I want all the solutions. I want to sample from this model. What is called, I think, exact sampling or perfect sampling. That is, I want each of these sequences to be out with the probability that it has in this strange constraint model, right? Okay. So do you agree that it's not trivial to do this? Yes, who disagrees? They don't. Cedric doesn't disagree.
It is
hard, right?
It's very hard, yes.
Well, this is very easy actually, because BP is polynomial, so I can sample this perfectly in real time. But in order to do this, and I can even show you, I have the code, because it's always better to have the code. In order to do this, I have to build the belief propagation graph. This is not something that transformers do. They cannot actually, because the context size is too long and it's in practice. Okay? So we can solve positional constraints with Markov models. It's polynomial, it's very fast, in real time. Do you want an example? I played an example yesterday. I will try to play it again. So I take the prelude, you know, the part prelude, and I generate, this is a track up there. I say, okay, I want to generate, I don't remember, 100 notes, but I want the thing to end by the ending of the prelude.
Oh.
Ah, that's hard. And I could have asked, please start by D or whatever. I could have asked a lot of different positional constraints. Everything is swallowed perfectly without any problem. So this is an example. Very nice, but very hard. This. So, okay, so I want to generate a simple prelude. I want to end by 10. And I want the thing to end by the ending of the prelude. Ah, that's hard. And I could have asked, please start by D or whatever. I could have asked a lot of different positional constraints. Everything is swallowed perfectly without any problem. So this is an example. nice. Transformers are way unable to do anything like that. Or, and that's actually a mystery for, I think, many people, they do it sometimes, which is even worse. So they kind of do it. So basically what the models do is that they have liquefied a constraint in the model, but we don't understand what they do. And I highly suspect that they don't do exact something anyway. They find some solutions. No way they can find solutions. Sorry?
What do you mean by exact sample?
I mean that when you sample n times, you have the probability for each sequence that you get, which is the probability of this sequence in the constraint model. So if the sequence is rare, it should be out rarely, you know.
So you have all the information about the probability.
Yes.
Not only R.
Yeah. I compute it. This is what the belief propagation is doing. But I'm talking about positional constraint, which is in fact quite simple. I mean, it's like this value is forbidden or is compulsory or that kind. So it's a unary factor, basically. Okay. Okay. So I want to show you something a bit funny, because for some time I used to use this example by Stefano Di Battista to say, oh, the guy improvises, and he's so good, he can, at the last note, I think there are 48 notes, or he can have the right note. And then I found another video of Stefano Di Battista, who is a great sax player, by the way, with other musicians playing the same tune, a different place, different year, and a different tempo.
Oh.
And then look at what he has done. This is the same as just show you. Okay. Another concert. Exactly the same phrase. So this is a trick like magicians should not say, but when you have a break that is so complex, they learn the phrase. Because no one's going to check. But anyway, the argument still holds.
So what was the difference?
There is no difference.
In fact,
So
it was not improvised.
Yes, it was learned. But
It was pseudo improvised.
don't tell me.
There is, but it's like in the, how to say, you know, in the classical music, the coda, some of them are
Yes,
written explicitly.
Yes, yes. But still, the argument, I guess you understand the argument, is very important because ChatGPT, for instance, many people try to impose unary constraint, and as you said, oh, it doesn't work. So what you said about Alexandra is different. This is meter. This is very interesting. In music, you have meter. So what is meter? So you have a bar. The music is divided into bars like this. Like here, I think you have 8 bars. Yes, 8 bars. And the music should be contained in those bars, right? It should not cross. It should not cross or here. And also, you have usually constraints about the bar transition. It's not nice to always have notes. I hear the notes seem to not care at all about the metric structure. Right? They go here, they continue, they start here, they start a little bit before. It's a mess from the, and then the thing ends a tiny bit before the end. It's absurd. And so the question is, how can you generate a Markov sequence where you know that the sum of the durations of all the guys here is going to be exactly number of bars, 8 times the number of beats, right? That's a difficult problem. Do you know how to solve this? Because it's called additive number theory. But do you understand why the problem is difficult? So I give you a set of notes, and each of them have durations. And you can put any number of notes, but of course they don't cross. So after a note, then you have to wait for the note to end, and then there is another note, and so forth. And I want the total number of all the durations to be exactly 32, for instance. Yes.
Is it a bit like an abstract problem?
No. Good try. It could be.
I was going to ask the same, so it's natural.
So it's a problem which is very interesting. It's called some set problem.
Why sunset?
Some set, sorry.
Oh, sunset.
So here you see it's a solution without meter, so it's messy, you know, there is no meter, and this is a solution with meter, and you can see that the node here, the field is exactly the same, and then all the nodes start, there is no node that crosses the bar lines, okay? It's even more difficult to do this. And remember, I have a Markov model, so I want to sample all the solutions that have this addition constraint. So meter is about summing durations, right? So you want to, so this is an example of something in the style of Michel Legrand. It's a MIDI. So you see, that's it. You feel the meter, right? There is no node going everywhere. So how do you do this?
So when you say in the style of Michel Legrand, it's with this...
The Markov model was trained on the Michel Legrand model. So why it is difficult? Because you can imagine that if you have 33 nodes, by the way, you don't know how many nodes, so it's another problem. But so suppose you know that there are 33 nodes, and each node here is a node plus a duration information. You have 13 million paths to explore. And you want to keep only the paths which are such that at the end the total duration is exactly 32 or whatever you want, right? It's difficult, right? No? Yes, sorry.
By the end, you mean anticipate cells positions?
Yeah, I mean 23 nodes, but you don't know where they are going to be in time. Just know that there are 23. But just an example.
What do you mean by nodes?
A node is one of
Yes, I
these.
mean,
So some of them are shorter.
specific positions to be moved by nodes, or what?
It's a Markov model, so it goes greedy from left to right. You add a node with some duration, and you add a node after, and so on.
Yes, but we have some restrictions about the nodes. I mean, regarding the tone that you're playing.
No, we don't care about the tone. Just focus on Markov plus durations.
So for every node, we have, let's say, all the possible
Transitions, Markov transitions,
Okay.
and then durations, but you want to add this constraint, which is a global constraint on the sum of the duration. And what is really funny, interesting, so you have a guy called Khovansky, I guess you know that guy, no? Oh, he did a theorem, which I think is phrased like this exactly. Basically, you have a finite set of integers. This is how I understand this. Well, I think it's very general, but you just have a plus, you have an addition, and you have stuff you can add. Then you are interested in HA, so that HA is the set of all the elements you get by summing elements of A H times. So A plus A is a set of all the sums of two arbitrary integers in A, okay, and 3A and so forth. And so the guy showed that the cardinality of this is a polynomial, which is a bit counterintuitive, because you could think that the more you add these numbers together, the more paths you get, which actually the 23 million I showed before, which is the intuition. But in fact, okay, the theorem is, I cannot prove it, it's quite hard, but it tells you that for some values of cardinality of A, its convergence is actually much less than what you think. So, thank you, Khovansky, because thanks to him, well, these 23 million paths will have only actually 13, which leads to different values. So this is manageable. You have only three different paths.
But
After 4 steps, it's not the same as before.
no, the total number is relatively small.
Okay.
But if it takes you enormous time to compute...
No, it does not, because that's the trick. That's
I mean, there are many problems. There is unique solution, but it's monster to compute it.
No, that's the trick, that we don't compute the path, which would be crazy. We just compute the sums of durations, which is much less. That's where, like, this is where AI and math is different, because we're interested in how we can do this quickly without spending time. But basically, this ensures you, this guarantees that you can reduce the search to something very small, which is polynomial in the size of the total number of different durations you have. Okay? So thanks to this, you can do meter in music. And you were talking about Alexandrin, but it's exactly the same. Alexandrin is meter. You have 12 syllables for each sentence. How can you, but the words have an unknown number of syllables. I don't have an example, but le train ne peut partir que les portes fermées. It's 12 syllables. But there are some words which have 1, 2, 3. You don't know in advance, and you have a recurrent model that goes from left to right. So how can you be sure that you are going to end on 12? It's hard. That's why ChatGPT is unable to do this perfectly. It does it sometimes, by chance, by some mystery that honestly I don't think we understand exactly why you can do it. But he definitely cannot do it well. He will miss a lot of solutions, he will favor some solutions and not others. He will not do exact something. This is what we want. Okay? I will skip this.
No, but it is good. It shows that you have a Greek collaboration.
Absolutely, Jason, Seculariu, very, yeah, I will come back to that if I have the time. So we generalize all this to say that any constraint that can be expressed as with a regular automaton, that is a regular language, actually can be sampled exactly with Markov. It's an interesting result because you can do a lot of stuff with polynomial time, even like real time. That's, I think, a very important. But unfortunately, you have Markov here, you don't have transformers. For transformers, as far as I know, there is strictly nothing that guarantees any kind of sampling under constraint. Okay. So now, are you tired or should I continue?
We are in good shape.
So I have lots of things to show you. This thing is about 1 over f noise. It's related. Everything I say here is related. Do you know 1 over f noise in? I will just present the beginning of this and not the end, because the end is about implementing this fast, right? So there is this thing about power laws. You know, you guys love these things. It has been discovered, I don't know, I think the beginning of the century, of the 20th century. So there are many phenomena that exhibit the same kind of power law when you look at the spectrum of the quantities that you observe. Basically, the spectrum varies like this. And alpha is more or less 1. So it has been observed in many things, the fluctuation of the Nile, music, language, stock markets. Mandelbrot has used this also to do a lot of stuff that I'm not able to explain, but obviously it's a well-known phenomenon, and physicists have tried to understand the origins. I don't understand the origins, but what I know is that human creations always exhibit that kind of power. So it's not a ranking 1 over, it's not a ranking 1 over f here, it's a spectral 1 over f. I'll give some examples. And then there is, so basically the spectrum is proportional to 1 over f. So this is a discrete and a continuous version. I'm interested in discrete. And so there is a guy, Richard Voss, who's a physicist in the 70s, I think. He did a very interesting experiment. So he took 3 values for alpha. Alpha is 0. So this is white noise, no correlation. Alpha is 2 Brownian noise. And alpha is 1, so 1 over f naught, which equals pink. Okay? And he generates, so these are examples of the spectrum you get. Random noise, Brownian, 1 over f, Brownian, okay? And you can check that it's 1 over f by computing 1 over f. And so what he has done is very nice. He has generated a melodies, notes. White melodies, brown, and 1 over f. So brown, it's easy, it's continuous path. Right? You know better than me what is a Brownian motion, right? And he has played this to many people and asked them what they think. Basically, This sounds very, very natural, musical, whatever it means. And this sounds totally random, and this sounds very Brownian, monophonic, monotonous, and stuff like that. Okay? So this is random. No correlation. Very boring. Sorry. Brownian. So Brownian means there is only small interval. So it's not very good, but there are some exceptions because, you know, I always have to talk about the Beatles here. So if you listen to...
What would you think if I sang a tune? Would you stand up and walk out on me?
It's locally Brownian. Okay.
Okay, it's not locally, yes, on the long term.
No, it's okay.
Everything is locally brown.
Sorry?
Everything is locally brown.
Okay.
Okay,
But
maybe
you see what
it's
I mean?
it's on a mesoscopic.
Yeah, mesoscopic, exactly. And this is one of our... Oh no, this is the wrong, sorry, the same, sorry. See, it exhibits some kind of stuff, a structure. We call it structure because we don't know how to call it. There is no structure, but it's just the frequency of the notes 1 over f makes it sound natural. Okay, it's interesting. Okay? And so,
It's a bit like this. Traduce par dessous.
yes, absolutely. This is the original paper by, because there is a Nature paper and JASA, the Journal of Acoustics. And if you look at the paper, it's very interesting because you see, these are examples of 1 over f. There is no bar lines. There is no bar lines. There is no metrics. First of all, it's hard to do metrics, but it's even harder to do metrics plus 1 over f. And it's even harder to do metric 1 over f and Markov, which is not what he's doing here. So this is why, and this I will skip because I can talk about it if you're interested. So what we have tried to do is to implement what we call the Voss constraint that can be added to Markov constraint, to all the other constraints, to produce music that is 1 over f. Okay. I will skip the complexity. By the way, I want to mention this because this originates from a paper that I read a long time ago by Gardner, Martin Gardner. And it was a very nice paper where he talked about that. And he gave an algorithm to generate 1 over f sequences. Do you know how to generate 1 over f sequences, by the way? Oh my God, you are going to fail the exam. So there is a very nice way. You take dice. Let's say you take 3 dice and you throw them. Okay. And each time, and at each iteration, you throw the you look at the changes. You look at the changes in binary notation with regard to the previous value that you have drawn. And if it's 0, you don't re-roll it. If it's 1, you re-roll it. And this, for some reason, which is a bit complex to prove, yields a 1 over f sequence, more or less. And what is really nice is that it's a very simple algorithm. And I think it's known that if you sum with a summation of Gaussians, which is well designed, you get that kind of things. I mean, it's not a worry. So basically what we did is to be inspired by this. We transformed this dice algorithm into a tree of some constraints, and we showed that this, in the end, gives you 1 over f sequences. I will skip all this and just so this is a sequence with there is no 1 over f, there is a GCC, which is a global cardinality constraint, where we impose a certain number of notes. And then what we show is that if you add the 1 over f, you have melodies, especially if you have 1 over f and meter, you have melodies which sound very natural. And I can give you many examples. What I want to emphasize here today is But I know that you are not very much
Okay,
concerned.
1 over f, so is this
No, more natural.
global constraint that you impose. So there is a Markov which is local in time, plus the 1 over f, plus some
Plus anything.
meter.
And so you get interesting stuff. And what I want to emphasize is that this cannot be done by transformers, obviously, but we are not playing the same game. We are not exploring the same space. We are exploring a space which is, from the viewpoint of probability, is less rich, less interesting, because Markov models capture much less than transformers or other models. But we are pushing these models to the limit by adding constraints of properties that make the thing more interesting. And so you don't have this with, you cannot have this with transformers, purely transformers, because they are not designed to do this simply. They cannot. Or just is a bit event with everything. Again, the sound is terrible. You see the little picture. It's not bad. If you want to hear very good examples, we have released an album called Hello World in 2018 with Skigger, and there are songs in this one is very, very good. And it's based on Insensatez. You know Insensatez? It's a song by Carlos Jobim, the king of Bossa Nova. And so it was trained on Insensatez, and it's also in the style of Bossa Nova in terms of harmony, and it's really very good. And these figures are all wrong because I think we have 13 million strings, which is wrong. Okay. Can I continue? Or are you tired?
We're
Good. I want to talk about palindromes. You know what is a palindrome? So the first sentence that was pronounced by a human was a palindrome. It was Madame, I am Adam. Okay. This one is very nice. Very nice because it makes a lot of sense. You can read it both ways, right? So palindrome is something you can read both ways. This is a very difficult problem. Why? For another reason. You have a kind of Markovianity. Well, we call it language, you know. After some words, there are words which are preferred. You know, after A, you don't have another A, for example. You know. But then you have a constraint that does not hold on words, that hold on characters. And the secondation of the word is not the same, of course. It cannot be the same both ways. So it's very hard because you have to deal at two levels at the same time. Actually, three. You have to deal at the level of the characters, the level of the words, and the level of Markovianity or whatever language model you have. There was no algorithm to do this so far. Oh, by the way, you can do this in music. This is the Bach Cherka. So you can play you can reverse it and play the two things together in fifths. It's not exactly about all.
Mozart piece, no? There's also a paradigmic short Mozart piece, no?
Probably. Mozart was not very good at combinatorial stuff. He was very bad at fugues. But fugues is a bit the same problem. You have a combinatorial dimension, which is really hard. This is a profound musical. Oops, sorry. Georges Perec, that you know very well, we talked about it last year, I think, wrote one of the most famous ones in French. This is just the beginning and the end, but you can see that trace inégale par un rôle is trace inégale par un rôle. So you see, and so the problem of these things is that it's extremely hard to do. Why? Because there is no algorithm. You cannot simply take a word, oh, I will take trace, and then try out some things. You know, there is no way you can do this. Give me an algorithm for this. It's hard, right? It's hard. I mean, I have to look for support. It's really hard.
Yes.
It's really hard.
So this is the letter written backwards.
Sorry?
This is the backwards reading of the letter.
No, this is the beginning, and I skipped, and the end it's like 2,000 words. Oh no, 1,000 words.
Yeah, this is the trace, and then you have the trace at the end.
Like this. So it's exactly the same.
So it can be read backwards.
Backwards, and when you read it backwards, you have exactly the same.
Oh wow.
And it's only the beginning and the end, because
Yeah,
actually
so this is a bit long. Now, if you speak French, you will see that the meaning is a bit borderline. Doesn't mean much, but it's French. It's syntactically correct.
it needs some poetic interpretation.
Yeah, exactly. Which is fine because we are French, so we have nonsense poetry. Okay. So a guy named Peter Morvig, an AI guy, he did a program that generates palindrome. This is one of them. It's just like words separated by commas, right? It's not very interesting, and moreover, his program is not very interesting. It's basically doing generate and test. I don't know. There is no guarantee at all. Okay. And there is no syntax here. There is no grammar or Markovianity if you want.
But you have also the manual plan.
Sorry?
You start the same as the Panama one.
A little bit, but not quite, yes. And so if you try a ChatGPT, please use O3, because O3 is the best currently to do search, to do anything related to search. It's better than the O4 and 4. And it's really interesting because you asked him, I could do the demo, but can you invent a palindrome from scratch? Because otherwise he will give you palindromes which are well known, like Élu, Marcel Crapeux, and others. And so what he does is that he tries a little more or less random stuff, and then he writes a program, Python, that basically compute the character string without removing everything which is not a letter, and he checks that this is equal to the same thing reversed in Python. And he tries with this, France, no, mon frère, no, France. And, oh, no, that doesn't work. This is what O3 does. It's actually quite smart. But there is no way you can find a big palindrome like by trial and error like that, right? So sometimes he will find some, but most of the time he will fail. And especially if you ask him to impose a word inside, he will usually not do it. So again, so what happens here is that, well, again, LLMs are absolutely not designed to solve any kind of combinatorial problem. And when they do, when they seem to do so, because there is like the chain of thought thing now, where ChatGPT gives the impression that he can have like argumented reasonings, it's still not doing things right and he cannot because it's not designed.
But have you tried DeepSeek?
Yes. No, I'm waiting for ChatGPT 5. Yes, we'll see. No, but I mean, my point here is that you can add as much chain of thought reasoning as you want. This is a deeply combinatorial problem. You will never do it.
No, of course, yes.
But I did try. I mean, we'll see. It's interesting. But what I'm claiming is that it's impossible with an LLM to do this. Sometimes this one works well. So we published a paper some time ago, 10 years ago. We proposed an algorithm that solves completely the problem in polynomial time and can generate all the palindromes, any size. And the way the constraint is Markov, so we take bigrams by Google, all the bigrams in English or in any language. So we want to have bigram, Markov order 1, plus the constraint of palindrome. It's very tricky. I mean, the result is quite simple. It's a bit tricky to understand, but it's based on what they call tensor products of graphs. It's a bit it gives headaches to understand what it does, but in the end, the algorithm is quite simple and it's very, very fast.
So you write all possible palindromes, and then you have to choose which ones we
Yeah, absolutely. But let me give you some examples. So, for instance, we take the Bible. But we enrich it with two bigrams, otherwise we don't have enough material, right? But we'd like to have palindromes about what there is in the Bible. I think the Bible talks about God, as far as I remember, no, not sure. So the Bible, these are the figures, you know. So 3 seconds, we build a graph, and we can generate thousands of palindromes. So for instance, we generated one, which is 84,000 words. We start by, did I say the old, blah, 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 the sin, poly, and then, this is the, okay. But what is interesting, what I want to emphasize here is that it's very fast, which means that there are algorithms to solve hard problems. Don't believe that LLMs, when they fail, it's because the problem is difficult. It's just because they are not able to do this. Okay, no, like a military art, but Cedric is here, so I will not talk about that. More interesting on migrants because you can reverse and do something different. So you can do, like, for instance, in one way it's in Spanish, and in the other way it's in French or something like that. Sorry.
Can you say a little bit about why you have to kind of double the graph?
Oh, that's really tricky. We can discuss after. Basically, it's really tricky because you have to. So basically, what we do with a graph where each letter is indexed. Each word is represented with the position of the letter in the word, and then there are tricks to be sure that when you read it both ways. But the thing is that once the graph is built, everything is instantaneous, as long as you want.
By the way, which languages are better for palindromes?
I don't know. Probably French is quite good. Because, I don't know. Oh, that's a good question. I don't know. So the question is, okay, we can do it for Markov, but how can we do this for? That would be great if we could do it with more language, content, and that would be great. That's a very hard problem, but that's the kind of problems that creative people like Perec are able to do, and not us, and not the computers. So now I have the choice. What time is it? I have the choice. I wanted initially to talk about Max entropy. Do you know Max entropy by heart? I guess, or not? Yes? No? Oh, I thought that all the physicists learned this as a first year, because I know. It's very interesting. Let me go through.
Look, all the people here, they love maximum and they love entropy.
Okay.
But not all are familiar with max entropy.
Let me, if you agree, talk a little bit. And again, I'm not a physicist. You should know better than me. But why we did this? It was a very. By the way, we did this with Jason Sakellariou, who is a great guy, but also Vittorio Loreto, who is a physicist in Sapienza, and other people. So the thing with Max entropy, I think, was invented in the 20s, 40s, 30s, I'm not sure. It's a very simple idea. It's okay. You have you want to find a distribution, a probability distribution, but you have only some observations about the moments of the distribution. For instance, you have the frequency of the elements, or you have the variance, or you have, as we will see, the pairwise frequencies. You know, this thing happens at the same, with this percentage of occurrence. So you have frequencies essentially, but things like that. And then you are interested in building the probability distribution that will have one sample which will have the same moments. But there are many. So you have the constraint that you want the one which also has the maximum entropy. Why? Because you want the one which has the less bias possible, which is the most random possible. Because maximum entropy is random. Okay, I'm going fast, but so you have constraints on the, let's say, I will show you which kind of, and then you want the one which has the maximum entropy. So this has been very, very well studied. So if you take, for instance, I think this somewhere the normal distribution is the distribution that has a given variance and mean with the maximum entropy. It's easy to prove.
And also to relate to other talks we've seen. this week, the constraint is the marginals, then the maximum entropy gives the factorized probability.
Yes, on top of it. Okay, so Jason he did his PhD with Marc Mézard, and he was studying the Potts model and Ising models. Do you know this Potts model, Ising model?
François, stop thinking that mathematicians know everything.
I thought you were.
I know you have something about mathematicians.
No, I like that. I am ashamed to be here.
Yeah, we know you are ashamed, but a good person for that is a good psychiatrist, not mathematician.
Thank you. Okay, so now we have music. We have music. We have the partita, violin partita. It's a sequence of notes, and we'd like to build a distribution, a probability distribution that spits out that kind of stuff again, like Markov model. But Markov model, you know, they don't do this kind of thing. Markov, they just capture transitions and that's it. You don't really know in the end what you're going to get. So here, what we look at is the frequencies of each value, each note, for instance. We have the frequency, we can estimate, we can count. And we also look at the frequencies of the pairwise frequencies. How many times these two values occur. And we have this kind of graph. So basically, so it's a translation invariant. So basically, we have a graph that has some order with k. Here it's 4. Sorry, here it's 2 because it's 2 on the left, 2 on the right, and this is the position, the central position. So at the end, you have 2 plus the 2k plus 1 on the sides. And we look at the frequencies, you know, of everyone, and also the pairwise frequency between this and this, this and this. But this and this and this and this is the same. This and this and this is the same. And this is the model we want to have. So there is a long tradition in physics to do this because there is a Ising model, but it's very ferromagnetism. You know, they want to model the interaction between particles, whatever, and they want to infer the global energy, for instance, like Hamiltonian or blah blah blah, and how it relates to interactions between particles. And it's a very hard problem because all the particles interact with all the particles, so it's intractable. So what they do usually is that they reduce it to binary interaction or maybe more and stuff like that, right? But what is absolutely, for me, absolutely beautiful in this story is that you start from really not much and you end up with something which is incredibly powerful. So this is the time where there is a little bit of that. So what we want to do, we want to find a distribution P that will yield these frequencies, unary and then binary frequencies for all pairs of values, nodes, like C and C sharp. But we want also that this property has a maximum entropy. Because this is very important, because otherwise there are lots of solutions which are very trivial and absolutely not interesting. Basically, you don't learn anything. I mean, learning in some sense is about finding the maximum entropy distribution. So what you do, you build a Lagrangian. Lagrangian.
Same thing.
So you say, okay, this is the entropy. You have the Lagrangian parameter for the
Lagrange multiplier.
plus multiplier, sorry. But this is important to note this lambda for the frequencies. So times the frequency of the model minus the frequencies that are observed. So you want this to be minimized, of course, and then the same for pairwise interactions. You can trust this is okay. You take the functional derivative. I think that you have many more methods which are more accurate to this. But basically, you want to find a probability that minimizes this thing. And when you differentiate, you get this, and you say it's equal to 0 because you want to minimize it. And you get exactly what I think you call the Boltzmann distribution. Oh, it's not a total coincidence, by the way, but it's really interesting because you get this without doing any other assumption. It's very beautiful. It's not only that. So you have a partition, you have to normalize. Okay, fine. So you know this. So the Hamiltonian, the energy, to call it probably, is the sum of unary, what they call local fields, or the U call, or they, I don't know, after we do, the local fields and the pairwise interaction, the binary interaction. Okay, so this is the total Lagrangian. And the probability is this. Fine, this is well known. This is absolutely ubiquitous. So you have no parameters, lambda and j, which, by the way, were the Lagrange multipliers. They have become. And so now the problem we have when you do AI, you have to compute these parameters. You have to estimate this. It turns out that we can do maximum likelihood estimation thanks to a trick, because the likelihood is a bit complicated, but we use a pseudo likelihood. We don't look at the whole sequence, we just look locally at the likelihood. So this is basically what we get. And there is a term, so this normalization term is to try to have the J as close to 0 as possible. There is more than I would say for practical reasons. I don't think it's that important. So basically, what you try to do, so what you have is, you have to try to minimize this, given the, and that is written here, okay? And the only thing I want to say, which is really nice, is that in that case, because it's a simple case, you can compute the gradient. You can compute the gradients of the Lagrangian with regards to all the parameters, the H, the local fields, you can compute them analytically. And with regards to the binary interaction. And you get something that's here, that's quite simple, in fact. It looks a bit I want to attract your attention that to compute this, you have 4 levels of a loop. You have K is going to be 10, okay. Is the size of the context. Actually, it will be 2 times K. So it will be 21. This K is 10. This is the vocabulary size squared. And this is the sequence, the training sequence size. Okay, so it's it's quite a big loop. This is in Python. Sorry for. So you have 4, 4, 4, 4. You have 4, 4. So it's going to be quite slow. But there will be a trick. We have a fast version that is extremely fast, but it's totally unreadable. I'm just saying this in case you are interested in trying by yourself, because it's very interesting to do it yourself on whatever kind of sequence. So the version here, I wrote this, it's pedagogical, you can understand it. The fast version is totally tricky, but it's exactly the same, it works the same. And then when you have all the gradient and stuff, you have one line of Python to minimize. That's it. The good nice thing about Python is that there are lots of libraries. Okay. Once you have computed your parameters, you can sample with Gibbs. Basically, you take a random position and you sample according to this, and you can compute this explicitly. And you do this a number of times until you think it's done.
Actually, there is some MCMC in this week.
But that's not, I don't think that there is anything special here. Well, there are some stuff, if you're interested, I can do some. When you do it in practice, it doesn't work so well, because there are always some elements which have not been through this thing enough. So at the last time I do a smoothing thing, it's really cooking recipes. But essentially we do this.
By a great chef.
Yes. So you observe, then we sample stuff, and you observe that you get exactly the frequencies that you want, the pair frequencies that you want. And there are interesting results also where we compare the Bax entropy with Markov. Obviously, Markov is not going to work well. Markov is not at all designed for that. Even with higher orders, you don't get the good. And then in the paper, we compare what you get. So we try to define the notion of style. So the goal is, okay, we take different composers, and then we sample all sorts of stuff, and we check that the samples are closer to the composer that they come from than to others, using some cross-entropy measurements that Vittorio Loreto has been a specialist of for a number of time, for quite some time. And it works very, very well, actually.
François,
Sorry.
Your start is already a whole sequence.
Yes, I start by a sequence.
So there are two notions of time. There is the time of the music, and there is the
So that's why
evolution.
here we don't care about time, because we consider that all the notes have the same duration. Because otherwise, but we could do it, because it's a bit of a pedagogical thing. But I will show you an example, if you want.
You do.
You do. So this is a partita by Bach, an existing one, a real one, by violin. Works. So you don't even have to play it. You can see the shape of the partita, the kind of thing going up and down, but of course, it's not as simple. And so now, I train with this. Training for this thing is, by the way, is quite long. It's this size, I think it's 2,000 notes. And I sample. Sounds like the thing. No?
It does.
But if you listen carefully, it's not working as well, because in the original there is a low frequency movement of harmonies, you know. It's going to modulate and come back, which here you don't capture, obviously. But you capture quite well the texture of the melody. Again, there is no time. Each note is just a pitch. There is no time here. We could put the time, you do what you want, you know, with the information. But if you have the time, obviously, you will need probably more data.
Excuse me,
Sorry.
can you explain a little bit when you say that this model is trained with the previous original, what information do you use from the original?
Exactly. I use the single frequencies of all the notes, which is counted only once, and the pairwise frequencies at distance k, for k equals 1 to 10.
So let's see that we understand well. In your Boltzmann stuff, there are these coefficients lambda and j.
Yes.
So you are finding the lambdas and j's
That
which maximize the entropy under the constraints of the frequency
Yes,
and of the pairwise frequencies.
absolutely, but I do this with maximum likelihood. So I do the lambdas and the h and the j that maximize the likelihood of the model to generate this thing.
Oh, okay.
May I ask so you have the original script,
Yes,
and each frequency has an endurance frequency, right?
what I call frequency is not spectral thing, it's the number of times each note appears in the whole thing.
Okay. So then, what is the relation of the final artificial, you know,
So this
to
is
the original one in one sense? I mean,
this is a training sequence, the original by Bach.
Yeah.
I get the P and I sample. This is one sample.
Yes, but do they have the same frequency?
Yes.
But maximal entropy in that sense we mentioned before?
The maximum entropy has nothing to do with the frequencies. It's one of the constraints is the frequency, another one is the maximum entropy. So this thing, among all the distribution that yield these frequencies, this is the one which has the maximum entropy, the most random one.
The one that you produce.
The one that I get, I show it, that I computed with all this mathematics likelihood.
Yes, it's exactly of the same kind of intellectual reasoning as when one does a maximum likelihood in statistics.
It is maximum likelihood, absolutely.
Yes, I have a question about the really confused number and the J's. So the J in the original Cox model is representing the interactions, right?
Yes.
So the J's that you find, these are like short range and localized interactions.
Distance K.
Sorry?
Distance K.
Distance scale.
I have as many J's as I have K's plus vocabulary size squared.
Okay, so this is kind of long.
It can be quite long. You can take quite long.
So I have a follow-up question. So in the box model, depending on the rate of your interaction, you can see these transitions.
Oh my God.
So I'm wondering if there is an analog of
Probably. But we don't generate huge sequences. So here, I cannot answer, I guess so, and there is no reason why. Because this is really the best you can do to model the sequence with that kind of model. I mean, the best one. It's a good question. But here, I was interested in just showing that you have models which are really, in physics, which are really interesting for this kind of stuff. But again, I encourage, if there are students here, I encourage you to try it yourself on sequences of stuff, whatever. So and I want to just conclude on this, this model with the H and the J's. In fact, it's like a neural network with one layer, more or less. It looks very much like, because you have the local fields are like the inputs or something like that, and then the binary are connections. So it's probably as powerful as a simple feed-forward neural network with one layer or two. But the big difference is that you understand exactly what parameter means. That's a very big difference. Okay. And that's why it's interesting. But also, of course, it is limited. It's less accurate than a transformer, but also it requires much less training data. The training data requirement, the number of parameters is again k times vocabulary squared. So it's smaller than what transformer would need. Okay. So here I can stop, or I can continue. But I think you are hungry, right? I can conclude on one interesting thing.
Very good.
Because in AI we like problems which are ill-defined. We are very good at that. And I invented with Pierre Roy, my colleague, a very interesting problem, which is the following. So you have two pieces. You see this as two piano roll, two sequences of notes. And you want to create a new piece that has the harmony of the first, the rhythm of the second one. The problem is, what is harmony, what is rhythm? So, vaguely we know what is harmony. Harmony is about the pitches of notes and the relation they have when they are together or not so far away, right? Something like that. The rhythm is related to the onset, where the note starts and when it ends. The duration, the onset, and maybe the interval between the note and the one after or before. That kind of stuff. But it's not very precise. So if you have a piano roll, you have a score, can you separate harmony from melody? Oh, I don't know. We are not able really to do this. But this is what we're trying to do anyway. This is the AI thing, We don't care about the problem, we want the solution directly. There is a guy, Serge Gainsbourg, who did a very good definition of harmony or rhythm. On the guitar, rhythm is the right hand and harmony is the left hand. It's probably the most precise definition you can get. You see why? Because on the right hand you decide when the notes are played, on the right and the left you decide which notes are played. But it's very hard to find a good representation. Anyway, this is the Brahms intermezzo. Kind of a break. Okay, so you get the and then you have a Schubert impromptu. Nothing to do, no relation. So we create Brahms rhythm, Schubert's harmony. So that works. It works really well. But we have an additional error. In music, by the way, Kahneman has talked about that. It's very interesting. Daniel Kahneman, the same guy. You know, when you go to a concert, it's great, it's fantastic, but at the very end, the guy makes a mistake. And then you go back home, and all your life, remember that the concert was terrible. And so Kahneman says, you have two selves, the experiencing self, this thing that is in time, the time, and the other one is, I don't know how to call it, the remembering self.
Remembering self.
And he says there is a tyranny of the remembering self on the experiencing self. So, but I say this because in those cases, you don't want any single error. So you do deep learning stuff, you have fantastic stuff with some errors. You kill the concert, right?
But so that your example shows well that performers know well the most important moments are beginning and end. These are the ones in which there is the biggest expectation.
Yes.
So mistakes in the middle are less important.
That's true, but we don't want any because, so that's the difference between, let's say, hard constraints. You want a system with a proof, maybe not of optimality, but you want a proof of coverage. You want to be sure to have all possible solutions, and you don't want to have anything that is wrong. So this is a problem I give to you actually as a. I can show you just a few examples. Last one. It's really fun. You play chords, jazz chords. Right? These things are not in Bach. And then you take songs which are many. Oh, sorry again, this guy. And so you notice that the matrix is not the same. This is graphs. The harmony is not like one bar. Sometimes it's one bar, sometimes it's two. So you can play whatever you want, and it will adapt to the harmony that is here. This is very nice. Jazz prelude. Oh, this is augmented chord. Never this. Okay, you get the idea? And you see you have retained the rhythm of the piece. That just changed the harmony. It's a difficult problem. Why? Because in harmony here, you don't have the same number of different pitches that you may have here. So you have to fill in the holes. Find more notes sometimes, or remove the right notes. So it's a difficult problem. Okay? Sorry, last one. I think this is the. Yeah. You know this song?
The diner on the corner.
This is the piano concerto.
I am sitting in the morning at the diner on the corner. I am waiting at the counter for the man to pour the coffee, and he fills it only halfway. And before I even argue, he is looking out the window at somebody coming in. I open up the paper, there's a story of the actor who had died while he was drinking. It was no one I had heard of, and I'm turning to the horoscope and looking for the funnies. And ultra bells of the cathedral, and it's time to catch the train.
I don't know how to stop this. This is my last slide. Now I will
Just maybe a few questions.
Sure.
Thank you very much for the nice and
Thank you for listening.
lectures. So, is there any questions?
If you know, I have a question before you, sorry. If you have an idea how to formalize the rhythm transfer problem in terms of like a well-defined problem of some sort, it's a minimization of distances, but we don't know the distances. I'm really interested. Okay, sorry.
Yeah, you said there like no mistakes. I guess how is that achieved?
Sorry,
You said there are no mistakes.
no mistakes?
You don't want any error.
No errors.
Oh, this is
How is that achieved?
this is achieved because our algorithm does not work by sampling a model in which we don't know what is in there, right? So the algorithm is, in some sense, well defined. So it does not, in order not to make mistakes. But the thing is, we solve the problem very well. We are not able to define exactly what's the problem in mathematical terms or in terms of distances.
So if it's not sampling, how is it doing?
Oh, it's looking at the harmony here, the harmony there, and trying to find a mapping that works. When you have the same number of nodes, it's trivial. The problem is when you have more nodes or less nodes, then you have to find which nodes to add or to remove. And so we have different heuristics. It's based on distances and stuff like this. There is no training there. There is no training because there is no data, by the way. So it's a pure algorithm.
You're just using one piece, two pieces, it's not
Yes. Yeah. It's one and one, a single shot learning, which I think is the thing that people need. The thing also I didn't say yesterday that when I showed the example with Bach and the transformer is that I cannot train it on the prelude. I have to put all the Bach monophonic pieces. So at the end, I don't know what's in there. You know? I don't know. That's a big problem of this model.
I would comment one theme of your talk is the variety of algorithms. You try to use for various problems, not trying to have one universal area to solve everything, which is a crazy approach actually.
Yes.
But the other, which kind of was implicit in your lecture, I guess, is throughout the algorithmic problem, try to understand better what it is we are doing.
Yes,
as humans. What is rhythm, what is this kind of things.
Yes, that's for sure. That's exactly what we're trying to do. But also, I think there is a grand goal. I mean, I didn't show because it's in a slide, but in the end, I would like to build a system that is a generative system, but that does not work by sampling a model. I have nothing against sampling, by the way, you know. But I want to build a model that is able to generate sequences with an intention, knowing why it generates this node and this. So there is just this thing. I'm inspired by this paper by Jacques Pittra, who was an AI pioneer in France, he's dead now. He published a paper in '77 in Artificial Intelligence Journal. It used to be the main journal for today. I don't know if it still exists. Anyway, people were interested in chess. I think it's a quite interesting idea. And you know, chess programs, they work, even today, they work by searching the space of positions. So you have the position of each piece, you have the configuration of the chessboard, and you search in this very, very, very large space. You know, at each turn there is about 35 possible moves. So if you want to go 10 moves, it's 35 to the power of 10, it's already millions of billions, so you cannot go there. It's very, very heavy. And so this guy has a very good idea in '77. He said, okay, let's not explore that space. Let's explore the space of plans. For instance, I want to get the queen. But in order to get the queen, I have to get rid of the cavalier, the horse. But in order to do this, I have to move my pawn and stuff like that. So the basic idea that the space of plans that you can build to get something is much, much, much smaller than the space of actual configurations by a huge factor. And so he built this program in '77, you can imagine. And this program was probably the best ever written. And And it's probably today, even today, better than any program. The problem of this program is that it did not do the openings and the endings, which is a totally different game, as you know. At that time, it was hard to do all this. But I think it's this kind of idea that we need today, which is to depart from these end-to-end systems where you start by a stupid prompt and at the end you have a complete signal without any intermediary representation. Because when you're trying to generate something interesting, usually you have some kind of plan, some kind of intention or something like that. I don't know exactly how to represent that, but if you don't have it, you are doomed to just sample a model that you don't understand. So, you know.
There are
works.
No, but I saw recently some people are trying to do some algorithms to make models of math problem solving, things like this, you know, like reasoning, whatever, by starting from a reasoning which is false and correct mistakes until finding a true reasoning.
Yeah.
But certainly for Alexandrian creation, this is how human proceeds. We start with the one that does not have the right number, and then we tweak people like Hugo who can do this like Popov, so it has to have a very fast algorithm because it's not exploring all the possibilities.
But we do this without guarantee that we have actually covered all the interesting possibilities.
Of course.
That's the problem. I think AI could do the same thing, but with more guarantees of coverage. That would be interesting. But maybe.
Okay, so thanks again, Francois. Thank you for your attention.
Thank you.
Just for the lecturers and for you, Habiba, meeting at 2 p.m. if you're available downstairs at the Olive Tree for a short visit of the campus. George.